Hi everyone, this is Mrs. J, and today we're going to talk about the indefinite integral and the net change theorem. Alright, so I've got some warm-ups for you to try, so please pause the video and hit play when you're ready to check. Alright, go ahead and check your work here. So really this is just how well do you remember some of your antiderivative or your derivative rules, which is really just the antiderivative rules backwards. Remember for all of these, we do need that constant of integration because these are just general antiderivatives. And then remember sometimes like for problems like part D, it's easier to rewrite the original function first and then take the general antiderivative. All right, I've got another warm-up here for you guys to take a look at. So again, please pause the video and give this one a try. All right, go ahead and check your work here. So for part A, we're doing a midpoint Riemann sum. So if we want 4 equal subdivisions, that means that each rectangle is going to have a width of 6. So I kind of divide it up into 4 rectangles, and I put a little arrow next to each midpoint. So we do 6 times r of 3 plus r of 9 plus r of 5 plus r of 15 plus r of 21. So that gives us 258.6 gallons, which if we're interpreting this is the amount of water that's flowed from t equals 0 to t equals 24. Now in part B, they ask, is there some time from 0 to 24 where our derivative, r prime of t equals 0? And we want to justify that with a mathematical theorem. So if you kind of look at your outputs here, you can see that they kind of slowly start going up and they definitely reach a maximum. We don't know if that maximum is exactly 11.4, but it does turn around and start decreasing. So just because we can kind of see that our function is doing something like this, we know that it is going to turn around and at some point r prime t then must equal 0. However, to show that mathematically, we can show that the slope of our secant line essentially from t equals 0 to t equals 24, since you'll see that we have the same outputs, that equals 0. So therefore, by MVT or actually Rolle's theorem, since it's equal to 0, there must be some value in between 0 and 24 where your first derivative is equal to 0. So we can kind of look at it and say, logically, I know that this must be happening. Then if I know that it's happening, how can I justify it mathematically? So again, you have to think way back to first semester when we learned about the mean value theorem or Rolle's theorem. All right, so here is a little overview of the fundamental theorem of calculus, part 1 and 2, that we learned about in the last lesson. So the first part says that if f is some continuous function over a to b and g is some function defined as the integral of f of t over a to x, then we know that g of x is also continuous and differentiable over that interval, and most importantly, g prime of t equals f of x. So essentially, if you take the derivative of an integral, they essentially cancel each other out. And then part 2 tells us how to evaluate an integral. So if we have the integral of f of x dx over a to b, it would essentially be f of b minus f of a, where this capital F represents the antiderivative of f, so f of b minus f of a. So just to make sure this skill is still fresh in our brain, we're going to evaluate a couple of definite integrals. So here we have the integral from -3 to -1 of 2 over x dx. So for this one, it might actually make it a little easier to use one of our properties of integrals and actually pull out our constant. And then it's just 1 over x dx. And now we can evaluate that integral. So we know that it's going to be 2 times, well, we know that the antiderivative of 1 over x is the natural log of the absolute value of x, evaluated from -3 to -1. So it's going to be 2 times the natural log of 1, because it's going to be the absolute value of -1 minus the natural log of +3, the absolute value of -3. So here we can actually use one of our properties of logarithms. We'll use that quotient property to rewrite this as 2 times the natural log of 1 over 3. And then we'll use our power property to rewrite this as natural log of 1/3 squared. So our final answer would just be the natural log of 1/9. All right, let's try another one together. So here, again, just like the last example, it might make it a little easier for us to take our constant, which is a 4, and move it out front. So rewrite it like this. And then the antiderivative might seem a little more obvious to you. So hopefully when you see 1 over t squared plus 1, you can see that that's the derivative of arctangent. So this becomes 4 times arctangent of x evaluated from 0 to 1. So that leaves us with 4 times the arctangent of 1 minus the arctangent of 0. So hopefully we remember our trig. So we know that the arctangent of 1 is pi over 4, and we know that the arctangent of 0 is 0. So that leaves us with 4 times pi over 4, which is just pi. All right, let's try another one together. So here we have the integral from 0 to 4 of e to the negative 2x dx. So when we think of this antiderivative, well, we know that the antiderivative of e to the x is e to the x, but here we have e to the negative 2x. So if we were to take the derivative of this, we would then have to apply the chain rule, and we would multiply it by negative 2. That's the derivative of negative 2x. So if we want our coefficient to remain 1, and we know we would multiply it by negative 2, then we know that this coefficient must be negative 1/2. And you could always check it on the side. So you could say, okay, let me make sure. What's the derivative of negative 1/2 e to the negative 2x? So we know that that would be negative 1/2 times e to the negative 2x times negative 2, which actually just gives us positive e to the negative 2x. So you could always double check it to make sure that your derivative is correct. Okay, and as we continue to evaluate this integral, it might make it a little easier just to pull out the negative 1/2, and then we can evaluate this portion at 4, so e to the negative 8 minus e to the power of 0. So we have negative 1/2 times e to the negative 8, and then we know that anything to the power of 0 is 1. So that leaves us with negative 1 over 2e to the 8th plus 1/2. All right, so now we have one where we're going to be using that fundamental theorem of calculus part 1, because we're finding the derivative of this integral. But you'll notice that this integral is from x to 2x of sine of t dt. So we know that our fundamental theorem of calculus only works when the interval is some constant to x, or some variable or some function here. So we have to get a little bit creative when we're looking at this one. So we can actually kind of split this up into 2 parts. We could say that this function y is equal to x, the integral from x to a of sine of t dt, plus the integral from a to 2x of sine of t dt. And we know that really if we put these together, if we're going from x to a and then a to 2x, it's just x to 2x. But I write it like this so we then can start using FTC part 1. However, you'll see something else is wrong. Well, not wrong. We can't quite work with it yet because here we have our constant on the top, but we can flip that by making our integral negative. So then we have negative a to x of sine of t dt plus the integral from a to 2x sine of t dt. And now we can use FTC part 1, and we can substitute this here and here and here. So y prime equals negative sine of x times dx plus the sine of 2x times the derivative of 2x. And then let's simplify this a little bit more. We know that the derivative of x is just going to equal 1. So we have negative sine of x, and then we know that the derivative of 2x is equal to 2, so plus 2 sine of 2x. And there you go. So there's kind of an interesting problem where you have to get a little creative with how you write your integrals, so we can then use the fundamental theorem of calculus part 1. Okay, so everything that we've been working with up until now has been what we call a definite integral. So you'll notice that on all of our integrals, we had that upper and lower boundaries are limits of integration. But now we're going to talk about the indefinite integral. So we learned from the fundamental theorem of calculus that an integral just essentially represents the antiderivative of the function. So the indefinite integral of f of x dx is just equal to capital F of x plus c, where this is the antiderivative of f of x. And you'll notice that here we do have our constant of integration, because really the indefinite integral kind of represents a set of all antiderivatives of a function f. So it's kind of like the family of functions rather than just a specific one. So that's why we have that constant of integration again. So now you can probably see why in our warm-up we practice finding the general antiderivative, because when we're finding these indefinite integrals, it's really just the general antiderivative. So let's try a couple more together. So here we have, we want to find the indefinite integral of 3 root x dx. So for this one, again, I'm usually going to pull out my constant just to make it a little bit easier for us. And then we can evaluate this integral. So we're still going to keep that constant. So we know that this is to the x to the power of 1/2. So if we're finding the antiderivative, it'd be x to the power of 3/2. And then we'll put a 2/3 out front. So when we apply the power rule, it gives us a coefficient of 1. So that leaves us with 2x to the 3/2. And then we have plus c. And there you go. All right, let's look at this next one. So here it might make it a little bit easier for us to rewrite this first before I actually look for the antiderivative. So if we have x times x to the 1/2, that gives us x to the 3/2. And so that's really just x to the negative 3/2 dx. So now if I'm doing the antiderivative of that, we know it's going to be x to the negative 1/2. And the way to make our coefficient 1, it would be to multiply the front by -2. And then we're just going to rewrite it. Well, we'll have our constant of integration, and then let's rewrite it so we don't have any negative exponents. So -2 over square root of x plus c. Or you could say over x to the 1/2. Either way is fine. All right, and for this last problem, I'm actually going to have us change this. I meant for this to say 1 over x in front. So go ahead and change that. So here, this is definitely going to be one of those problems where it's much easier to rewrite the function before we try to find the indefinite integral. So I'm going to distribute the 1 over x. So we have the integral of 1 over x plus 2x cubed dx, and now I can find the antiderivative of each individual part. So we know the antiderivative of 1 over x is the natural log of the absolute value of x. And then for this next portion, this would be x to the 4th. So in order to get a coefficient of 2, we're going to want to put 1/2 out front, and then we have the plus c for our constant of integration. All right, let's try 2 more together. So here we're going to find the antiderivative of each individual part. So for the t squared, we know that it'd be t cubed, but the way we would get a coefficient of 1 would have a 1/3 out front. And if we want to end up with negative sign, well, that's just the actual derivative of just regular cosine. So it's just plus cosine of t, and then we have plus c. There we go. And then for this last one, we have the integral of cosine of x over 3 dx. So here we know that the derivative of sine is cosine, but then we would have sine of x over 3. That can't change, but we know that we would then do chain rule and we'd take the derivative of x over 3, which is 1/3. So in order to get a coefficient of 1 here, we would need to multiply this by 3, because 3 times 1/3 is 1, and then we just add our constant of integration and we are good to go. All right, and here again is just a list of a table of indefinite integrals. So it's just those general antiderivatives that we talked about at the end of last semester. And really, it's just your derivative rules, but backwards. Maybe one to look out for would be the integral of 1 over x dx. Remember, it's the natural log of absolute value of x, just because we need to make sure that this value is always positive for a natural log to be defined. And then this one is also kind of useful to keep in mind. If you have the integral of a to the x, we know that the derivative of a to the x is a to the x natural log of a. So if you don't want to have a natural log in your final answer, then we have to divide by the natural log of a here. So those are, the two to kind of look out for. But again, it's all just your derivative rules backwards, but they're here kind of summarized in this table in case you need a little refresher. All right, the last thing we're going to talk about in this video is more of a conceptual application of our integrals, and that's the net change theorem. So the net change theorem says that the definite integral on the interval a to b for a rate of change function represents the net change of the antiderivative function over the interval a to b. So here you could see this is essentially just the fundamental theorem of calculus part 2, right? We're evaluating a definite integral, but you can see that it's f of b minus f of a. So if you're taking the n value and you're subtracting the initial value, that would be the net change of our antiderivative function. So I want to look at some of the examples or applications of our net change of functions in science and social sciences. So let's take a scenario where the volume of water being pumped through a pump station is given by the function v of t. Then that means that the rate of the flow of the water would be v prime of t. Remember, the first derivative represents the rate of change of the original function, and this would be in gallons per hour. Then if we have the integral from t1 to t2 of v prime of t dt, well, we know that the antiderivative of v prime of t would be v of t, and then if we evaluate that using our fundamental theorem of calculus, part 2, it'd be v of t2 minus v of t1. So what does that mean in real life? Well, that would be the net change in volume from T1 to T2. So it's essentially your volume at T2, and then you're subtracting the volume from T1, and that would be in gallons. All right, let's look at this next example. Here it says if the cost of producing X refrigerators is C of X, then the marginal cost, remember way back to first semester, marginal cost is also an application of our first derivative. So that would be C prime of X in dollars per unit. So that's the cost of producing the next unit after. So then we have the integral from 4 to 13 of C prime of X dx. Well, we know that the antiderivative of C prime is just C. So it'd be C of 13 minus C of 4. So if you think about what that means, it's the cost of making 13 minus the cost of the first 4. So if you're taking away the cost of the first 4, then this would represent the total cost in dollars of producing the 5th through 13th refrigerator. So notice again, in this case, it's the 5th through the 13th because we're doing the cost of all 13 minus the cost of the first 4. So it's the 5th through the 13th cost. So just a different application of our net change theorem. So now just to kind of help us review some of the concepts from last semester and to kind of tie it all together, we'll kind of look at the relationship between the position, velocity, and acceleration functions again. So remember, s of t always represents our position function. So we know that, well, if we were to take the integral of s of t dt, it would just be that antiderivative. So that doesn't have a specific name to that. We'll just call it s of t. But if we have the velocity function, well, we know that velocity is the first derivative of our position function. So if we were to take the integral of our velocity function, it's actually just our position function. And then we still have the plus c because we always need that constant of integration when we have our indefinite integral. And then if we're thinking of acceleration, we know that acceleration is the first derivative of velocity. It's the rate of change of velocity, which would make it the second derivative of position. So if we were to take the integral of our acceleration function, we know that the antiderivative of acceleration would be velocity. And we know that if we were to take the second integral, kind of an interesting concept of our acceleration function, it would be our position function because position is acceleration is the second derivative of position. So if we're taking the second integral of acceleration, it gives us position. So again, it's just kind of tying together these concepts of position, velocity, and acceleration and how that would apply with our indefinite integrals. So now I want to take a moment and talk about the difference between displacement and total distance traveled and how that relates to our integrals. So here, if we have our the integral from t1 to t2 of dt, we know that the antiderivative of velocity is position. So it would just be s of t2 minus s of t1. So if you think about what that actually means, s of t2, that would just be our end position. And s of t1 would just be our starting position. So if we're doing our end position minus our start position, that just gives us the net change or the displacement. So displacement is it's different from the total distance traveled. Again, it's simply your end position minus your start position. Now, if we think about this integral in terms of the graph above, so this is our velocity graph here. Remember, if we're taking the integral of it, it's the area under the curve. So this area, the area is under your curve or between your curve and the x-axis. The area is the distance. So if we were to evaluate this integral using this graph, we know that it would be a1, and it's positive because here it's above the x-axis, but then here you'll notice that it's below the x-axis, so it's actually minus a2 and then plus a3. So we are taking into account the fact that this is moving now in the negative direction. Whenever velocity is negative, remember it means that your particle is moving in the negative direction. So this would be the representation of this integral. Now here you'll see that we have the integral again from t1 to t2, but this time it says the absolute value of velocity. So it's essentially making sure that all of your function is going to be above the x-axis. So the part that it would really affect would be this portion right here for a2, and then imagine that it was flipped to this side of our graph. So if we were to evaluate this, then we would have a1 plus a2 plus a3. So since we're treating all of the movement kind of as positive movement, that actually gives us the total distance traveled. So again, when you're just evaluating a velocity function and you don't have the absolute value there, that's just going to represent the displacement because anything that's below will take away from the distance traveled because it is negative. However, if you are taking the integral of the absolute value of our velocity function, anything that was in the negative direction is going to be counted as positive, so that will give us the total distance that your particle traveled. All right, so now let's see if we can kind of tie all of this together and try an application-based problem. So this says the velocity of a particle is given by this function v of t equals t squared minus 3t plus 2 for whenever t is greater than or equal to 0. So first, let's quickly talk about when is our particle moving right, left, and when is it stopped. So we know that our particle is going to be moving right whenever our velocity is positive, because that's the positive direction. And we know that's moving left whenever our velocity function is negative. And we know that our particle is stopped or at rest whenever our velocity is equal to 0. So we can solve that by doing a quick factor. So we could do t minus 2 times t minus 1. So it's our critical points would be when t is 1 and 2. So next we do a little sign analysis. So here's our left endpoint, and then we have 1 and 2, and we can evaluate where our factors are positive and negative. So between 0 and 1, both of our factors are going to be negative, resulting in a positive here. And between 1 and 2, this will be positive, but this will be negative, resulting in a negative. And then anything to the right of 2, both will be positive, resulting in a positive. So we can see that our particle is moving to the right from 0 to 1 and from 2 to infinity seconds. And it's moving to the left from 1 to 2 seconds, and it's stopped when t equals 1 and when t equals 2. All right, next we're going to find the displacement of the object from 0 to 3 seconds. So we know that if we want to find displacement, it's the integral from, it'll be from 0 to 3 of our velocity function. So we can evaluate this. We know it's just going to be s of 3 minus s of 0. We know our position function is the antiderivative of velocity. So let's find the antiderivative of this function here. So it'd be 1/3 t cubed minus 3 over 2t squared plus 2t. Remember, we don't need our constant of integration when we're evaluating a definite integral like this. So that will equal, if we plug in 3 first, we get 9 minus 27 halves plus 6, and then minus 0, so that we end up getting 3 over 2. And then I'll just say units because that wasn't defined for us in the problem. All right, before we move on to part C, I want us to kind of visualize what's going on. It will help us with part C actually. So just so we can see what our velocity function looks like, here's 1, here's 2, and then here's 3, our endpoint. We know that from 0 to 1, our velocity function is positive, so it's above the x-axis, so something like this. We know that from 1 to 2, it's negative, so it's below. And then we know that from 2 to infinity, it's positive. So it looks, I don't know, something like this. So what we did was we did a1, and then we did a minus a2, and then plus a3. That's how we would find that definite integral, because remember, anything below the x-axis we count as negative when we're finding the area under the curve. So here's what we did here. But if we want to find the total distance traveled, here we go, like they're asking in part C. So here we want to find the total distance traveled. We really need to make sure to address this A2. So again, when we're finding that total distance, it's going to be the integral from 0 to 3 of the absolute value of v of t dt. So the way we can achieve that, we can kind of split it up into 3 parts. So we know it's from 0 to 1. That's one of our segments. And then we have the 1 to 2. And then we have the 2 to 3. And then the one thing, again, we need to make sure that this area ends up being positive. So then we'll just take the absolute value of whatever this area is, because we know this will give us a negative result, and then we just want to make it positive. So now we're going to evaluate those individual areas separately. So we still have that same antiderivative, so we've already found that, plus 2t, and we're going to evaluate that from 0 to 1. And then we're going to evaluate it again from 1 to 2, and then make it positive. So remember to put the absolute values around that. And then we're going to evaluate it from 2 to 3. So same antiderivative. And again, evaluated from 2 to 3. Okay, so now we just start plugging through. So for this first one, we get 1/3 minus 3/2 plus 2 minus 0. So we have all of that. Plus, and then again, that will all be absolute value of, here we have 8/3 minus 6 plus 4 minus 1/3 minus 3/2 plus 2. Again, absolute value of that, because we know that that portion is negative, so we want to make sure it ends up being positive. And then we have plus, let's see, 27/3 minus 27/2 plus 6 minus 8/3 minus 6 plus 4. And then we're just going to kind of keep plugging through. So way to the left, this gives us, so we have 5, 6 plus the absolute value of, we have 2/3 minus 5, 6. And then we have plus 3/2 minus 2/3. So that gives us 5, 6 plus 1, 6 once we take the absolute value of it, and then plus 5, 6, and that gives us 11, 6, and then we'll say units. So here, it's really important that we can kind of understand what our velocity function looks like, so we know when the velocity function is below the x-axis, because that will be the region that we need to watch out for, make sure that it's positive. But again, that's only when we're finding the total distance traveled. If you're just finding the displacement, it's just the indefinite integral between your two endpoints. All right, so that is all for today's video. Thank you so much for watching.